induction motor slip and its significance, and we are going to discuss the necessity of starter which is connected in star delta connection for the induction motor. So the difference between the synchronous speed and the actual speed of the rotor is known as the slip speed. So normally we write this as the difference between slip speed is ns minus n. So the induction motor works on the concept of mutual induction, which we discussed previously, and the EMF responsible for producing the torque is induced in the rotor and not supplied externally like DC motor. So the supply, stator supply produces a rotating magnetic field which rotates at synchronous speed ns is equal to 120 F by P. So, according to the Lenz's law, the induced EMF in the rotor will produce a current to counter the source of change, because it will oppose the cause producing it. The cause is nothing but the supply voltage or the source. So, hence the rotor starts chasing the rotating magnetic field. It always tries to catch up the speed of the synchronous speed of the rotating magnetic field. So at start, when n is equal to 0, s is equal to 1. When you apply the n is equal to 0 for the equation ns minus n divided by ns, that is s is equal to ns minus n. When you apply n is equal to 0, s is equal to 1. So the stationary rotor has maximum relative motion with respect to RMF. So hence maximum EMF gets induced in the rotor at start when S is equal to 1. Now, when n is equal to 0, so when n is equal to ns, s is equal to 0. So when s is equal to 0, eventually the motor will not start. So it will not possible for the induction motor to uh, to run. So this is ns minus n by ns is called the slip is called the fractional slip or the absolute slip. So we also gave n is equal to ns of 1 minus s. That means the rotor speed is equal to the synchronous speed into 1 minus the slip frequency, 1 minus the slip. So the rotor speed will always be less than the synchronous speed. So because of the above phenomenon, so n is always less than a synchronous speed, so it is also called a subsynchronous speed. So generally the slip has to be between the 5 to 6% in large motors and 8 to 9% in small motors. Now, what is the frequency of the rotor current? So when rotor is at standstill, so when the rotor is at standstill means when the motor is not running, the frequency of the rotor current is equal to supply frequency. So at standstill, the frequency of rotor current is equal to supply frequency. When there is a relative speed between the stator field and rotor, then only there is a slip. So at standstill, S is equal to 0, the when it is not running. So when there is a relative speed, S is equal to 1. So induced EMF varies with the rotor speed. So what we have, Ns is equal to 120 F by P. So we know that Ns is equal to 120 F by P. And we also have the synchronous speed Ns minus N is equal to S. So Ns minus N is equal to S. So that is the slip of the rotor frequency. So which is given as 120 Fr or F dash by P. So Fr, or you can also write as F dash. So what you can write here now, if you equate Ns minus N by Ns will be equal to, if you write the equations for ns and n, so what we get here is ns minus n is equal to the slip, so slip is equal to 120 fr by p divided by 120 f by p. So relative frequency, this is called s. So s is 120 fr by p. So what we get here is 120 f by p. So we get pp get cancels 120. So s is equal to, we have fr by f. So the rotor frequency is nothing but slip times of the supply frequency. So, so we have fr or f dash is equal to s of f. That is equal to supply times of the frequency. Now, what is the necessity of the starter? Depends on the slip of the induction motor. Slip of the induction motor. So at start, the value of slip is at maximum equal to unity. So the rotor current will be normally I2 will be equal to E2, that is induced EMF in the rotor, divided by square root of R2 square plus X2 square at S is equal to 1. So we told at start at S is equal to 1. So when you give this equation, if you observe, the E2 is the rotor induced EMF per phase at start. So at start, EMF induced in the rotor circuit is maximum. Therefore, I2 is also maximum. So as the rotor current is high at start, consequently stator will draw high current of order of 5 to 8 times the full load current of the start. So when it is drawing 5 to 8 times of the full load current, so there will be a possibility of damaging the motor winding. And similarly, due to inrush of current, other appliances connected to the line may also get subjected to voltage spikes, may also get affected. And this initial rush of current 5 to 8 times is mainly because of the absence of back EMF. So to avoid such necessary limit current, to limit this current, so we have to initially start the motor at a very less current. So we need to limit this current at the starting. So thereby we need to insert certain resistance into the motor at the time of starting. So we introduce a starter at the starting of the supply connected to the induction motor. We include a starter. So starters will not only limit the starting current but also provide protection to the induction motor against overloading and low voltage conditions. So large starting current, as I said, may cause damage to motor. Motor connected to three-phase lines may get damaged, and other protective devices also may get damaged. There might be a voltage drop because of the more current. And in squirrel cage induction motor, rotor is permanently short circuited, so it will damage the winding. So we have to apply the reduced voltage at the time of starting, and once the motor is having sufficient load, then the motor can draw more current, so which may not damage the winding of the motor. So a star delta starter is the most commonly used method for starting of a three-phase induction motor. So in star delta, starting an induction motor is connected in through a star connection through the starting period, because in star connection, in star, so we know v phase is equal to vl by root 3, but il is equal to I phase in star. In delta, uh, v phase is equal to vl and I phase is equal to il by root 3. So that means if you observe, when it is starting connected and star means there is a reduced phase voltage, and thereby there is a reduced EMF, and thereby the initial current I2 can also be reduced. So in star delta, starting an induction motor is connected in through star because of this advantage. That is, during star connection, the voltage is reduced by 1/3 of the line voltage. So once the motor reaches the required speed, the motor is connected in through delta. So we use the automatic switching. So if you observe here, there is a star delta type of reduced voltage starter. We use it to reduce the starting current, as I said. So it will reduce 1/3 of the inrush current. So at that starting, it will be in start, and during the normal running condition, it is connected in delta. So as I said, the phase voltage will be reduced by 1/3 of the line voltage. So changeover switch is of double throw type. So for initially the switch will be thrown to star at the time of starting, and the switch will be thrown to delta at the time of normal running condition once it attains 80% of its speed. So review questions: explain slip and its significance, explain star delta starter. So the difference between synchronous speed and actual speed is called slip. So normally at the time of starting, there will be inrush of current, which is 5 to 7 times of the normal current.